cubed over 3 plus x squared between 1 and 3, right? So you get 27, 9 plus 9 plus 9, 18, minus 1/3 plus 1. And so 17, 16 and 2/3. It's 16 and 2/3 foot-pounds. Okay, makes sense. Okay. So it's just the usual game of calculus, right? You want to do something that you're not really sure how to calculate it, so you chop your problem up into small discrete pieces, and then you say, oh, well, for each of these pieces, I know what the answer is, right? Each piece is just going to be x squared, x squared plus 2x times it's going to be the force times the distance. And then you add up all those things and take the limit, and you get some integral, right? It's almost like a philosophy of how to deal with problems, right? You don't know how to deal with a problem, chop it up into small pieces each of which you know how to do, and then somehow take a limit of that problem. That's the hard part, I think, in reality. Is everyone following this? Okay, let's do a harder one. Okay, so there is a tank of water, and the tank is in the shape of a cone. Okay. The cone is 4 meters radius up here, and it's 10 meters height. And the tank is full up to the 8th meter. Okay. So up until the 8th meter, it's full of water. So the thing is full of water up until the 8th meter. They tell you that the density of water is 1,000 grams per meter squared. A meter cubed, excuse me. Okay, and then they'd like to know how much work does it take to pump the water out? Pump the water to the top, right? So every bit of water, you're gonna lift it up to the top, lift it up to the top of the tank, okay, to pump it out, basically. Okay. I'll let you think about it for a minute. Think about how you might do it. Yeah, think about how you might do it, right? How you would chop this thing up into pieces, right? How much work it would take to move each of those pieces to the top, right? Okay, so think about that. How would somebody gives you this problem, how would you do it? Using the calculus philosophy of, approximating with this thing by pieces, okay, and then taking the limit. Feel free to talk with each other. Talk with each other and see if you can figure it out. Okay, so let me just ask first, how do you want to chop this thing up? How do you want to chop the water up? How are you going to chop the water? Yeah, in slices, right? So you're going to slice you're gonna chop it up into things that like this, right? Because each of those slices, all the water in there is going to have to move the same distance, right? So you wouldn't want to chop it into some sort of vertical slice, right? Because then some of the water moves less distance and some of the water moves more distance, and that just makes it more complicated. So let's cut it like this. Let's call. You can set up an axis. So this is. Let's call this the x-axis. Okay, this will be the x-axis, and it's going downwards. Okay. Okay. So we cut at some distance x from the top, right?
I was thinking about another way.
Oh yeah, how were you thinking?
Then I deny myself.
You what?
Then I deny it.
Okay. Okay. So you cut at this height, right? And so we need to find the we need to find the weight of that thing, right? So right, we're cutting at a distance x. We're cutting at a distance x. We have some tiny height, right? We have some tiny height delta x, right? There'll be some radius. There'll be some radius r, right? And the volume is going to be what, pi r squared times dx, right? Pi r squared dx, and then the weight is going to be the density. Let's call this thing delta. It's going to be the delta times pi r squared dx. Okay, density, right? Everybody seeing this, right? You take the the volume is going to be pi r squared, right, times dx. That'll be the volume, and then the weight of that thing will be, right, this is all water, so you take the volume times the density, and that gives you how heavy it is. Right, that gives you the that gives you the weight of it. Okay, so let's see. So okay, so remember that this is 4, and this thing is 10, right? This thing is 10. So we can actually get an expression for r, right? How are we going to get what r is? What's r in terms of x? Okay. 2 over 5, right? So, right, you have similar triangles, right? If this is x, and this is 10, right, and this is 4, and this is r, right, then we know that 4 is to 10 as r is to 10 minus x, right? If this is x, then this is 10 minus x. Right? So what's r? R is going to be 2/5 of 10 minus x. Okay. So the weight then is going to be this 1,000 pi 2/5 squared 10 minus x squared dx. Right? And we need to move that, right? The work that's done by moving that to the top is going to be this weight, this force times x, the distance, right? How far do we move it? We move it x, right? So the work for that one chunk of water is going to be x times this thing here. So right. So whatever that is, you get 1,000 times 2/5 squared pi x 10 minus x, squared, right? 10 minus x quantity squared dx, right? That's the work for that one piece, and then you take the integral of that. You take the integral of that from 2 to 10, right? Because the initial height, the total height here was 8, so you need to take from x equals 2 all the way down to x equals 10, right? So total work equals the integral from 2 to 10 of that, right? So so that's the amount of work you need to do to move all the water out. Yeah.
Why is it integral from 2 to 10?
Well,
Why
what do you think the integral should be from?
Integral from 8 to 10.
From 8 to 10? So that would be right. So 0. Remember how we set up our axis, right? What's x? X is the distance from the top. Right? X is the distance from the top. So when x is 8, right, that's down here, right? X is 8, x is 10. Here x is 2. x is 0, right? And we're asking how much work is it to move this whole block of water to the top, right? Well, we have to take all those blocks from 2 up to 10 all the way to the top. We can't start at 8. If we take from 8 to 10, that'll just be this small bit down here. Okay. Okay, everybody okay with this example? Okay, we'll do one more example of work. This one is easier, actually. This has to do with springs. So you have a spring. Okay, and there's something called Hooke's law, which says that the force needed to maintain a spring stretched x units beyond its natural length is proportional to x. Is proportional to x. Okay, so the force is equal to some constant times x. Okay. So, you know, if you pull it a little bit, then the force needed, you need to hold it there, is not that much. But if you pull it farther, that force increases depending on linearly on the length, right? So if I pull it, if it's rest here and I pull it 1 unit, that'll require a certain amount of force. If I pull it 2 units, that will require double that amount. And pull it 3 units, it'll require triple that amount. Right? It's directly proportional to the distance, right? Okay, so that, you know, if you pull it 10 times, then that'll take 10 times as much force to maintain. Okay, so that's this thing, Hooke's law. Okay, so this is just an observation about springs. Okay, but we'll use it to figure out some information, figure out some precise calculations. Okay, so okay, so here's the example. You have a spring, and it's 10 centimeters long. Okay, so it's naturally 10 centimeters. Okay, and they say that a force of 40 newtons is needed to stretch it from to 15 centimeters. Okay. How much work is needed to stretch it from 15 centimeters to 18 centimeters? Okay, and so the example goes like this. You say, well, look, you know, 40 newtons is needed to stretch it 5 centimeters, right? So this is what you see, right? 40 newtons for 5 centimeters, right? 40 newtons for 5 centimeters. So what does that tell you? That K times 0.05 meters is 40 newtons, right? K times 5 centimeters is 40 newtons, right? And so what does that tell you? that K is going to be 40 over 0.05, so that's 800, whatever it is, newtons divided by meters. Okay, so you figured out, right? We know what our spring constant is, right? This thing K is called the spring constant. The spring constant. Okay. Okay, so you figure out what K is, and then you play the game, right? How much work is needed to stretch from 15 to 18? Oh, you say, okay, well, it's the same thing, right? If I need to move it a little bit, I'm going to have that force times that distance, right? Right? Again, you can chop, say, okay, suppose this is 15 and this is 18, right? To move it a little bit, to move it from here to here, 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 right? You break it up into little chunks, and you say, well, I'm going to need 800 xi times delta x for each one of those things, and you sum of those guys from I equals 1 to n, right? And then you take the limit, and you get the integral from so 15 centimeters to 18 centimeters. Right? 800 x dx. Oh, no, I'm sorry. Right. This should be 0.05 to 0.08. 0.05 to 0.08, right? Because the spring, when it's at rest, is at 10, right? The spring, the natural length of this spring is 10. So you're going from you've stretched it 5 centimeters and you're trying to stretch it to 8 centimeters. So this should be 0.05 to 0.08 meters. Okay. Right, and then so you work that out, right? And you get 800 x squared over 2 between 0.05 and 0.08, and you get some answer there. Okay, so yeah, so this is application of calculus to the notion of work, right? So simple work, if the force is constant, then it's just the force times the distance. But if the force is variable, right? Here, as you're pulling harder, as you pull farther, the force is changing, right? If your force is variable, then you need to do this approximation, right? And then take the limit and then get the answer. Okay. So you approximate your problem, with some sort of Riemann sum, and then you take the limit, and then you get an integral, you integrate, and that gives you the actual answer. Okay. So this is typical of how you use calculus in physics in mechanics. Okay, let's take a break. Take a break.